Hello everyone and welcome. Today we are diving into the how to use ks-nav for feasible and meaningful test campaign in the Linux kernel. Sound thrilling, doesn't it? Okay, maybe not yet, but stick with me. I promise to keep it as painless as possible, and who knows, we might even have a little bit of fun during the way. Here the agenda for today. I won't go over each item now. You can scan it faster than I can explain it. So, ready to dig in? Let me introduce ks-nav for the few that are not sick yet of hearing me speaking about it. It is a toolset designed to analyze the Linux kernel binary and generates diagrams that make sense of its complexity. If you ever try to dive into the kernel internal, you know it is like starting into the abyss. ks-nav helps bring some clarity. But wait, why analyze the binary when you have the source code? Great question. And the answer is because the source code is like that one friend that over-explains everything. Source code is full of macros, compiler's quirk, and build step that can make your analysis really complex. Instead, analyzing the binary skips all the drama and gets straight to what's really going on. It's like skipping the director's cut and watching the actual movie. Now, let's talk about testing. More specifically, why coverage-based testing isn't always the hero we think it is. Sure, seeing an high coverage percentage feels great. It's like getting the Mario Gold Star. But here's the catch. While tools like ks-nav can isolate coverage for a single process, the problem lies elsewhere. The current test suite, like LTP and kself-test, are just not designed with ks-nav in mind. Even if we had a perfect per-process coverage, we'll still face the bigger problem. High coverage doesn't guarantee that crucial paths are being tested. What we care about isn't just lines of code that were executed. It is which lines are crucial to the functionality we are verifying. This is why tools like ftrace are so valuable. They let us trace execution specifically for a test campaign, cutting through all the noise. Alright, let's walk through how ks-nav fits into the testing puzzle. The first step is highlight the difference between what could happen in the kernel and what actually does happen during the test. On the left, we see the static call tree. This is what ks-nav brings into the table. It analyzes the kernel binary and gives us a complete map of all theoretically reachable paths for a given API. Think of it as the map of possibilities. But here's where things get interesting. Not every path in this map is crucial for our goals. This is where human expertise comes in. We need people, not just tools, to define safe critical paths. ks-nav helps here by simplifying the coder structure, making it easier for experts to zero in on what matters most. It is not automagic. It is a partnership between the tools and the human brain. Now, let's overlay the test execution. Tools like ftrace generate runtime call flow based on what exactly gets executed during the test. This gives us the map of reality. The real power came when we compare these two maps, the static call tree and the runtime data. ks-nav ensures we can match the critical paths identified by experts against the execution data. This lets confirm whether the critical paths were hit. Let's dive into the indirect call issue, a topic that might sound familiar to some of you attending my past talks on ks-nav. For those who are new, don't worry. we are starting at the root of the cause here. Indirect calls are a fundamental part of the Linux kernel design, especially in its driver-based architecture. This call delegates the execution to functions determined only at runtime, making them highly dynamic and flexible. But for tools like ks-nav, they are a nightmare, because the target of the call isn't immediately visible in the binary or in the source code. It is resolved only on the fly at runtime. And this can get even worse. In some architecture, indirect calls are obfuscated partially to mitigate vulnerabilities like Spectre. Have you ever heard about Reptoline? Now, let's look on how indirect calls impact the work of ks-nav. The diagram you see here illustrates the problem quite clearly. On one side, we have a static call tree generated by ks-nav. On the other, an actual execution trace from a test run. Noticing something odd? There are functions in the execution trait that aren't in the static call trace. These alien functions are the downstream effect of indirect calls, functions that ks-nav currently can't predict when building diagrams. So, while generic software analysis tools may hit a hole here, the Linux kernel gives a Unix edge, because in any given build, all possible code paths exist in the binary. This means that although we can pinpoint exactly what call happened at runtime, we can enumerate all the possible targets. There are plans to extract this information from source code, but for now it is not a thing yet. More on this on the plans for future. For now, we have a workaround, ftrace log. This log captures the runtime resolution of the indirect call, allowing us to rerun ks-nav with this additional information. This approach amends our diagrams, bridging the gaps caused by indirect calls. Let us dive into the root cause beyond ftrace limitation, and why they are so tricky to address. First, there's an assumption I start with. If a function appears in the call all seams, and it isn't marked as no instr, I expect it to show up in the available filter function. Logical, right? Unfortunately, that's not the whole story. Not every function listed in call seams ends up instrumented for ftrace. Why? Compiler behavior throws a wrench into the work. For ftrace to log a function, the compiler must explicitly insert the instrumentation code. But here's the kicker. Compiler optimization can silently remove or bypass the instrumentation. And here's the real challenge. Once the kernel is built, these omissions are effectively set in stone. In short, ftrace limitations are less about the tool itself and more about the complex interaction between the kernel build process and the compiler. Now, let's talk about what happened when ftrace dropped the ball, or rather, the function. First, ftrace misses some function entirely. When that happens, they vanish from the log. The result? Holes in the goal graph. Suddenly, functions that should be connected are showing up as isolated, lonely nodes with node parents. And for this use case, we might end up in seeing missing arches that suggest not execution, which is not how things are gone. Check out the image. The diff between call seams and available filter function highlight what is missing. And on the graph, those graphs create a disconnected subgraph, breaking the flow and making the analysis less reliable. Is there a solution? As a matter of fact, there are many. One, for example, would be compile the kernel using flags that makes this event unlikely. But this is not always an option. Instead, what is always possible to do is to use the info from the ks-nav database to fill up the gap. High interdependency in the kernel function makes simplify calls tree a real puzzle. Imagine trying simplify a graph by removing certain node, like spotting a kmalloc and decide to skip diving into the memory allocators. In theory, it sounds great. Cut the node, drops its children, move on. But here's the catch. This is not a tree. It is a graph. And in this graph, there is a dense core of functions so interconnected that starting one means that you can end up in almost everywhere else. Take, for example, the execv shown here. For any given starting point of the call graph, the size of the reachable subgraph is shown, and about 1/3 of the function is tightly linked together. This level of interdependency make collapsing sections automatically or isolating domains nearly impossible without losing critical insight. GraphTool, the next component I'll include in the ks-nav toolset, support a couple of strategies to address simplification and avoid complication brought by this high interdependency. For those who know me, you'll know I never let a presentation go without a video. So here's the video for today. So, in this video, I dare to suggest using ks-nav to better understand what our kernel tests actually do. Let me be honest, kernel call trays are huge. ks-nav can provide this trace and it has some basic filtering capabilities, but they are limited. Sometimes, they're just not enough to handle the sheer size of data. To address this, I've been working on a command line tool to manipulate this graph. It is not rocket science, but it is something you really need if you want to go down this path. Before diving into the main topic, let me introduce the tools we'll be using in this session. First up, ks-nav. I assume most of you are familiar with it. I've been preaching about the ELISA audience like a true evangelist, but for those who aren't yet acquainted, let me provide a quick practical overview to supplement what I've mentioned in the earlier slides. In this session, I'll be running ks-nav remotely, not because it needs, just because the machine that had the guy here has not the database permission set up. As you can see, it is a plenty of options. Most are conveniently stored in a configuration file to save us from specify a long command lines. ks-nav is the trusty graph generator for our kernel traces. Now, I love ks-nav. How could I not? I wrote it. In Italy, we have a saying that sounds just like this. Innkeeper, how's the wine? And the innkeeper always replies, the wine is excellent. So, as its creator, I'm definitely biased here. That say, ks-nav filtering is minimal. If I really want to bore you properly, demonstrate you thoroughly, I need an additional tool with more advanced filtering capabilities. This brings me to the second tool, which is a work in progress. It has a few functions, but I won't show you all. It's not the focus of this session. We'll only look at the one we'll actually use. Alright, after a lengthy introduction, let's get to the meat of the matter. Assume we want to test whether all critical paths in the execv are covered by our test. ks-nav can give us a static view of all the functions that can be called. But for syscall, this graph is massive. Let's see how this massive really means. That's 9054 edges between functions, and the number of nodes 3678 nodes. A single graph like this is unusable. Let me show what it looks like. This is the complete plain execva call tree graph. It is terrible. What you're looking at is essentially a cloudy fog made up of an overwhelming number of arcs. There's no discernible pattern, and in this form is practically unusable. Visualizing something this chaotic doesn't help us gain insight. It only highlights how crucial and effective is filtering and clustering for understanding the data. Yeah, not great. To make this usable, I attempted to cluster the graph. There's a wealth of research on network community detection, identifying cluster and related nodes. I tried using the Lovian algorithm, a well-known cluster method. I must say it is impressive on test graph. But on this monster, after running it for an entire day, it was still chugging along, with no clue on how much progress it had made. So I tried to cheat it a bit and use the more natural decomposition, the maintainer file suggested subsystem. By focusing on this kernel subsystem, I could achieve a usable view in a reasonable time. It is not the natural speed. It took around 4 minutes, which is a huge improvement over the 164 minutes it took me to print the whole graph unclustered we seen just before. Here you can see a partitioned graph. It is huge, but that's not a surprise. We already knew this. In the graph, you'll notice boxes. These boxes represent subsystem, while the vertical green stripes are actually arches that connect different subsystems. One obvious observation is that the kernel is highly interconnected internally. The boundaries between subsystems aren't clearly defined. In fact, the only interface that is consistently respected is the scope within individual compiler units. Let me wander around this picture for a moment to give you a sense of how deeply interconnected the kernel is. About the result, this is barely usable, but the previous was not at all, so I would say it is a fair improvement. For this session, I'll decide we'll use a partial graph produced with a limited depth exploration. They allow me to show the essence without the full complexity. We need two ingredients: the possible function space and the actual execution path. Here's an example. Next, let's take an example of test trace. The log resembles a graph format, but isn't quite there. Let's convert it to a proper graph. Here you can see the ftrace log transformed into a graph. One thing that immediately stands out is how much cleaner this diagram appears compared to the static view from ks-nav. The reason for this is fairly straightforward. In this case, we are only visualizing the paths that are actually executed. Conceptually, it's much closer to a tree derived from the graph. Now we can compare the static ks-nav graph to this runtime trace. A note on the color we will see. So, orange are nodes unique to the ks-nav graph, which means function not executed. The blue are nodes unique to the ftrace graph, likely interrupt or prior execution. The purple are common paths. This look good overall, but there is an example where the expectation didn't match the reality. For instance, this load_elf_binary should have been in both execution space and possible function, but ks-nav struggles with indirect calls. Let's fix it manually for now. First, fetch the load elf binary graph. Then connect it to execv graph. Let's compare it again. This is the updated graph. Let me take a moment to show you the change. Now, I need to find the load elf something. Where it could be hiding? You think searching would be simple, right? But no, of course not. It's like trying to find your keys when you are already late, and they have somehow decided to teleport into another dimension. Let's call through this jungle of symbol. Here we go. Oh, wait, no, it's not. Maybe I could just use this search feature. Should work with partial name too. That would be neat, wouldn't it? Alright, got it. Here's the load elf binary. It really didn't want to be fun today. The final step is enabling safety expert to define critical paths and validate them. ks-nav can assist here also. We can split the graph into manageable chunks for expert view. For example, let's explore how subsystems interact, and let's see the first subsystem encountered in this trace. If we want to focus on the subsystem composition, here it is. Don't let all the labels and connection overwhelm you. The concept here is actually pretty straightforward. The yellow subsystem connects to the others through this function. If needed, the expert can zoom in and focus exclusively on a single subsystem. Here's an example where we were looking at the internal details of a subsystem, along with its internal connection to other parts. This view helps to isolate what's happening inside while still keeping the broader context visible. This process can be iterated over the subsystem that have an interest, and ks-nav can map them to hide the navigation. This final diagram is the subsystem map. It serves as a guide to identify which subsystem need to be examined further. By following this, experts can systematically decide where to focus in their attention for analysis. So, these are the building blocks. While we don't cover a full use case here, this laid the foundation for future work. Stay tuned. So now we reach the point in which I make the promise for the future. ks-nav has come a long way, but let me tell you, there is still plenty of work ahead, and plenty of opportunities for anyone itching to contribute. The good news? We are not starting from scratch. The ideas are there, some early steps have been already taken, and the roadmap, it is also there, but with no dates. Take the indirect call handling. Right now, calls are like locked door in the middle of the call tree. The plan will pry that door open by extracting call position from the binary, digging into the debug info, using libclang to trace the potential target from source. And for ftrace logs, they got their quirks too. The missing parent-child links for one. The plan is to use ks-nav database to reconnect those dots. And finally, general improvements. Adding a web-based interface to make navigating all this graph more intuitive. Personally, I'm a big fan of the graph feeds layout. But for speed and interactivity, we also exploring the JavaScript-based tools like bits.js. And we reach the end of this presentation. Thank you for watching.